Cool. Let everybody's spirits running like that. The early mornings get harder and harder as we get going. So thanks for being here. From what was starting to do the first part of this discussion in the first week, I will review what we did. And we had so many like good conversations and questions. We only got so far. I was really thrilled about that. I'm enthusiastic to have more questions and discussions. We had to talk about that. Talk about some things out. Probably make sure about the last 5-10 minutes while we're in there, I'll probably make sure I get through the rest of the pieces that I want to make sure to mention, because I imagine there'll be conversations that come out. So at that point, I might start to just accelerate. See fair? Yeah, cool. So cool. So the whole session was just generally talking about sort of the physical computing, energy efficiency, and lots of stuff that we can keep them up to. So it's kind of good stuff when we think about it here. What we talked about last time, maybe I'll just make sure I get a summary of this. And I'll talk about this. Start off with quickly. There's lots of depths. We had a whole talk, but we can keep going. We can ask questions on this as well. The thought in terms of the energy efficiency, really came back to the original point that when I go back to the 80s and early 90s, the question you never wanted to be asked was, why did you just do this on DSP? And that more to know their digital things over time. And there's a long history there where our group has been on anchoring that, particularly being at Georgia Tech and so forth. It's sort of really the first really good answer is something that when I usually talk about is reverse hypothesis, which is basically saying, digital really can be sort of energy efficiency can be a factor of thousands or thousands more than the analog side or than the digital side. There was more stuff on neuromorphic there. Bobena even mentioned some of that, yay. But just this alone was very significant. There's a couple different ways people came into working this, and we started hitting this from different edges. Certainly, without question, the definitive thing in 2004, doing this in vector matrix multiplication. And what was really interesting about, in terms of, that was clear there, as we've hit digital, it's hit the sort of energy efficiency wall. There's been I think there's a whole more range of opportunity. And so we can actually start talking about, how far did we get on the digital side? And there's lots of things we bounded these conversations. The analog side, that factor of thousands there, but then the neuromorphic should be even further than that.
So where are we up to on this?
So this is a graph that came out of the Neural Roadmap paper about 2013.
Okay.
And if you look at from the very first digital sort of things to sort of roughly the energy efficiency, well, that was about a factor of 1,000 or more energy efficiency improvement. MAC, by the way, for those who don't know, that is multiply accumulate. So adding MAC is million multiplied accumulate. The reason we anchored to that was two reasons. One, a lot of this was tied to the early DSP conversation, so they were very careful about enumerating that way. Number two, you want to compare apples to apples and things. Everyone who does computer architecture knows you always use ops because you have a whole mixture of what you mean by ops. So you can play all sorts of games on your numbers when you talk about ops. So I don't use it because it's not a fair unit.
But MMAC is the same thing.
It is a couple of ops, but you have to be careful who talks about ops and what they need in their grouping of ops.
It's like multiplied here. You can use maybe 4P1 to get it.
Actually, there are some specifics on what this means in review. For which, so most NMAC, yes, you could actually have an NMAC of 16, 8, 4 bits, 32 bits, so on. We can talk about. There is also discussions of there's sort of nice roughly quadratic scaling between adding bits on multiplier MAC units. Sessions that we can go back and review that. Yeah. So we just be very, very careful. But it is very true that classic approach is that people have been trying to reduce the bit number size down because that's one way you get some of the energy efficiency back. The original measure on the energy efficiency wall was that everything normalized 32 bits. The 32-bit element, that way you can actually compare apples to apples when you did that. And there's some history behind where that came from as well. Cool. Okay, so So the thing that gave us the ability to, at the time, and I think it's still very good technology for doing the MMAC, for doing the matrix vector multiplication for floating gates. Yes, I do lots of floating gates. Those who don't already remember. The beautiful thing about this is we've done an NCMOS process. It's also very nice because I can then, it basically says, look, I can take a transistor and I can move this IV curve anywhere I want, which you can say is a shift in threshold, but if you're on the sub-threshold side, it feels like a multiplicative factor. It's really kind of nice because it basically involves a transistor and a set of capacitors to that gate material. And you want to make sure that there are no contacts in the gate material. And if you do so, then you get these kind of lifetimes that are 10 years, I guess somewhere between 10 to 100 microvolt height and shifts over 10 years. 10 years is important because that's the longest any IC is typically rated for. So what it really means is I program it in factory, and when I end of life, it's shifted by that amount. And you might go, well, say it's 100 microvolts. How much does that mean for a subthreshold current? Real quickly, and it's less than 1% shift over that 10-year lifetime, which works pretty well actually. So it's strangely enough, there isn't a lot of magic in how this gets used. Obviously, you might go, how do you change the charge? And that's always interesting combination of electron injection, electron tunneling. That requires a bit more physics to get into that portion. But if you want to know that, please ask me. I will enjoy that greatly.
Did you use them say recording in progress? Because I want to make sure you're being recorded. I'm sure it is. And just usually I hear it in the morning.
You're not above. Yep, it's recorded.
I'm very sorry. I just wanted to make sure.
Thank you. Thank you for checking. So we talked about the, again, good having this good. Again, you can talk about this sort of being a vector matrix multiplication. Again, almost tiling in elements here. Basically, we would use these like current sources, which then allows me to play off the transconductance voltage and current out. And again, we did talk about this, but if you need me to slow down, I'll slow down. Which then, if I attempt to look at the current summation is ideal. And then as a result, so which is Kirchhoff's current law. Nice when your math is actually a law. And this turns out as a result to give you a sum over that, which is vector matrix multiplication. So this sort of nice element, which is single transistor, started from this old single transistor lining synapse concept. Really thinking about it this way, now 30 years ago, would allow you to do this. This whole conversation, if you think about it, is like, wait, this looks like a crossbar of memory elements that I'm computing through. Yes, indeed, that's when we think about it, and that's kind of the genesis of where computing in memory, the real original naming of it came out of, because it's not just the fact of computing in a nice dense mesh architecture. If I look at it compared to digital, I have to then get everything, out of the memory, into the processor, and back. So I might compare this computation, but I still got everything else here that can get me in trouble. So communication can be very expensive. In fact, often be more expensive, far more expensive than the actual computation. I believe something Andreas has advocated for many times, and I wholeheartedly agree with that.
Jen, saying this, you and Anna didn't kind of resolve, because that was around the communication, wasn't it? And
It was.
I wonder if you wanted to say a few words about that.
I might actually a little bit later. Okay, but thank you so much for giving that. No, there is a cost of communication, and in fact, you can make an argument if you're looking at sort of the analog architecture concept, and you can actually generalize that quite well now. That you could almost just make the argument of, I think a couple of people in this room have also made this comment, that, just assume that computing is free and everything is in communication and communication to memory. If you do that, actually, a lot of times that gives you a good initial bounds actually of the system. So that tends to be very important. And so from that, this gives us into all sorts of, different things you can build, including adaptive filters. This was 20 years ago stuff. That also gets me into all these, FPA kind of concepts, which is based on this combination of logic, routing, and analog elements with IOs and so forth. So these are very important. These are devices that are kind of important here. For those who, may or may not be familiar with FPGAs, remember that it's routing and logic, digital lines, so it can be actually, when you say logic, the logic these days can even be a small processor embedded on it. It can be a whole bunch of stuff, right? Multiply units and so forth. So, and where you look at this, usually the foundation when you get into this question compared, and then all the FTA stuff can come along with it, is that you're dealing with things in what is typically Manhattan routing. This is actually very important. And I don't know how many people are familiar with the Manhattan routing infrastructure, but it's basically take your CLBs, if they're digital, if they're analog, they're cabs, and you can have mixtures of this. These are effectively, this is like your building, these are like your streets, these are like your intersections. And so you basically get the data on the street, it then turns or goes forward or goes in certain directions. Question that we're getting. What's important about this whole architecture is it was designed for digital circuits. It is actually the key reason why FPGAs became all viable. Because you tend to think, oh, it's logic and routing, so it must be a bunch of logic and a crossbar, right? Turns out if you do that, then it's scaled and squared quadratically. That's kind of a problem. So what they realize is like, well, what kind of architecture can I use? And this kind of an architecture is really well suited if you're dealing with things that are local and sparse. Because very good local connectivity works well, and I can get some sparse connections as I do work out here as well. Very interesting when we start to then move this to an analog space, because I can then start talking about things that are local and sparse and different computing I want to do. You want to build some hot-tail networks, and I have local and sparse things depending on the kind of structure. It's also very true in neuroscience, right, where almost the entire structures tend to be local and sparse. If you know, a good rule of thumb is almost every single size scale of neurons, roughly, and I know I'm generalizing here a bit, but it's roughly about 6 to 8% of the axons leave that space. Most 90, which means 92 to 94%, never leave that area, which means it is by construction a local and sparse. So a group of 1,000 neurons to the cortical column, a grouping of layer, on and on. And that sparsity, I think, is very important, not because you couldn't make every line, but you don't have the energy to do all that communication. You will die. You just don't have the energy to make that communication all the way, even in human cortex. So
I know actually, but that's the difference between biology and silicon is find out biology is about 10,000.
yeah,
And in silicon, your typical body is 10. So you got 1,000.
yes, agreed.
So that changes the game. And as so unless we address it's as way as in and I guess I feel what the silicon can't be able to.
I think there's two concepts there that you said, because in general, I pretty much agreed with it, but I want to make sure I read it properly. So yes, the communication versus computing makes a lot of sense just because of, in many cases, it is that routing when the connection matters. I would also agree that typically in digital structures, which is one good example, the fan is a lot lower than typically neurons. But that doesn't mean we shouldn't be taking some interesting inspiration from these concepts. This doesn't mean that I couldn't actually make some of my networks, some of my analog networks, some of my networks of neurons this way, and there could be some advantages. It also very clearly, by the way, on the digital side, if you do it this way, they know that this then scales not order in squared, but order in. And that's helping to tiling things as
So it's so to access that the metrics that make sense is everything that has to do with odds and webs and millimeter square. That's really what matters, because we can make a JB analog multiplier that's JB as opposed to carrying on is long multiplier, but the carry that's where the energy.
it's a nice.
Anyway,
I mean, there's certainly no disagreement on the importance of communication and how much that drives the energy efficiency of the whole system and so forth.
that's not chemistry.
It's true. Yeah, no disagreement. Not disagreement. That it can very much be an important issue. Not sure what the other multiplier comment was, but I'll let that sit.
Is there anything to be learned from the fact that neurons don't have all of this family blazing directly at the sun? It's in this complex structure.
I think for many neurons, there's probably some truth to that. Although I think in some sense, there's more than just connectivity with the dendritic.
So that's part of this distributed process. And I don't think our current approaches in another digital on the other side would really have a distributed process.
Picture it in a similar direction what Andreas was saying. So when I was at Frommerhill, we were building a chip or starting to build a chip, then a stage like stretched up like networks of spiky neurons. And the big discussion we always had is exactly like a question of fan in and fan out, because the number of wires explodes, right? And like the n squared number, I'm not sure exactly where this comes from, but there's the finding like as you scale it up, right, you have longer distances and you have more neurons that you want to connect, right?
Yeah.
There's really lots. So for us, I think we ended up with like 1,000 neurons, 25 in like in degree of synchronizing. And I'm wondering, like, is there a way to go to bigger networks? Like, is there something where I think this is
Right.
Yeah.
No, I think that, I mean, fair point. And to try to reiterate what you said, so other people who are hearing it also understand it. I mean, I think there's always the need of saying, hey, I want to go to bigger and bigger networks, right? The order n squared, by the way, is about just a raw crossbar. So that scale order n squared, and that has its trouble. But you want to go to bigger and bigger networks, right? And you want to go to bigger and bigger, you want the neurons to have and so forth. The question that becomes, though, am I also thinking about the neurons as being very local and sparse, which we know, again, from the anatomy, it's true, right? And also in terms of energetically, that seems to be what you have to do in terms of energy. And it's actually an interesting article. It was out of the original roadmap paper that we did 2013, 11 years ago. Everything in that, I think, still holds. Sounds cool. But the key is that you just look at the entire energy of the brain, say, order of it's for communication, order to 30% for communication on energy. You start to say, what's the average total length of an axon that I can have? I mean, with all of its branches and everything. And what you get is about a number that's about 25 centimeters or 25 millimeters. And you go, when you top to bottom on the parameter cells, about 7 meters, crap. So, I mean, yes, there are ones that are very long, but on average, in terms of just energetic use, you have to be very careful. And that's assuming best case numbers. You go through that in great detail. And so it turns out you have to be careful, and the locality and sparseness are essential. Just in terms of, otherwise we have to eat 5 times as much, which I guess I can do that, but maybe in human history, that's not been the case. Instead, I think there's something there important. That's cheap.
And also there is, you should take everything that's logically inspired, because there are things like routing it in standard it's a small world network.
Yeah.
Connectivity is constant, is about 6 degrees, right? That you can use a hierarchical type of route.
Yeah, and so depending on what it is you're building, that makes sense. I just find it interesting that you can see some things both in terms of actual engineered solutions and biological solutions. And there's a reason here. Does it solve everything? No. But it does give you some interesting insight to how you think about some of these questions.
And I get as far as the argument, but in biology, you still have to spread the number of like those synapses. And it's of course having backup, for example, like the vector sonic architecture stuff or whatever. You do actually get like 1,000 inputs or something, but you want to do a dot product in layers. Yeah, it's so. Is there a way to, is there a limit like that? Because I've seen a lot of crossbars in analog, and they're always like 16, 64, or 256. Like maybe if I'm not playing it, but it's always in the range. So I'm wondering out there.
It's on the technology, and I mean, certainly we built things bigger than that. But it's not just about building a crossbar. It's not about building a crossbar. I mean, to build this infrastructure, each of these have its own kind of different crossbar pieces.
The crossbar, making a bigger crossbar, I think Mike just set out crossbars at 100,000. My friends, 500 ones like 500. The problem is not the crossbar, because the crossbar is tiny. Taking the data to the crossbar, you need cache memories. And if you have an area there, a quarter of the area is the crossbar, and the other 3/4 is the cache memory to feed the data to keep the crossbar.
Well, and there are some people who run the architectures that way, and I think the ideal thing is you do not want to be caching a lot of stuff, because as soon as you build a memory, there goes your communication problem again.
Well, unfortunately, there's something called computer architecture that
Yes.
this is where you're building neuromorphic or non-neuromorphic. You have to pay attention to it, and if you don't pay attention, you
Clearly,
make something totally useless.
but Andreas, clearly you have to pay attention to it, but it
Yes.
doesn't mean you don't minimize it when you keep. Now, there's good reasons to do that. I mean, yes, you have to pay attention to it, no question. Absolutely, absolutely agree with you.
And imagine in these flash technologies, including on the good, the average utilization of flash versus everything else about 10%. When you buy a flash drive, it's a die that stores all your memory. 10% of that is Jennifer's analog arrays, and 90% of that is everything has at least support that 10%. So you're gonna get difficulty scaling away from that 10, 11, 13, we give 14 on of our chips. So area matters.
Area matters.
It doesn't have to be a commercial product that uses flash memory like the stuff that you're doing. Funny images.
I agree, and a very rare flash memory die is what they look like, and the core of the dies are still mostly the memory because that's usually what you're competing on.
I can show it with the macros, commercial macros.
And that you can look at these things.
Part 3 of our talks, and it's part 3.
No, we're going to try it. It's fine. We should talk more about it. I would love to have these conversations.
I'm a little bit cynical about everything, so it's okay to that.
Okay, sure.
Maybe the more constructive question than just like, what was the architecture around the analog?
Yeah. So we're getting there.
Okay.
Cool.
And if you have,
Cool. I finally bouncing. So, and then I should.
I'll be arrived.
Yes.
I told you you want.
And so, yeah, so then the last slide, and thanks, just reviewing from the last time, was the fact that, this is sort of how this setup starts to work. And this is kind of like how our typical kind of structures was a picture. I'll say actually a little more what was in here in a moment, but definitely sort of meshed these boards. This is definitely actually that laptop with basically everything should I can control everything. One analog discovery in the loop here to kind of just do the instrumentation. There's a whole tool infrastructure as well with these FPAs and a whole range of different kind of board structures into this. I'm going to kind of peel back parts of this as we go, but I figured I sort of ended with this picture last time, so I figured I'd make sure this was still here, but we're going to get back to this. So now we get to continue.
Oh, this is part 2. That was part 1.
I was just reviewing the last time, but okay, I love the questions. This is great. Okay, we're good. We're good so far? Okay, good. All right, so then we get a little deeper into, okay, so what do we mean on the FBA structure? And cool. So, this is kind of where the sort of the system on chip SoC kind of FPA family over the last, we've been really working with this concepts of chips pretty much over the last decade, or 8 to 9 years probably now, internally. The core of the chip, if you actually look at what's in there a little bit, when we put this whole thing together, there are definitely blocks for analog components that actually have routing. There are different components in here. There are examples of transistors, capacitors that are floating. There's plenty of capacitors to ground if you like. So we have to work off that. They're T-gates. There are transconductance amplifiers, but what's also nice is the current sources are actually programmed internally. There's actually a couple different flavors of these, one of which are floating gate inputs and ones that don't. I'll explain a little more of that as we see an example of that. But what's also in here is that, and that's where all the A's are, there actually are digital blocks in here. So we actually built full, 8 BLE kind of structures with a D flip-flop in there. And the first thing everyone goes, wait, you got your analog and your digital interdigitized. You're not supposed to do that. Analog here, digital here, never touch. It turns out actually it actually works just fine on the routing infrastructure. We spent a bit of time getting that right, which is very nice in that whole, this is all top level from that Manhattan infrastructure. But there's a lot of times I want the digital run with my analog. For example, if I'm going to compile, let's say, certain varieties of analog to digital converters, I want some digital with my analog right there. So I'm just going to put it right there. And once you start to go, hey, wait, I don't actually have to have the separation, you begin to realize there's a lot of things you can kind of flow between the two of them. Clearly, in this FPGA part, we're typically not trying to compile a processor because, after all, I also built hardcore of that in here too. This is 16-bit hardcore. The reasoning for that, one is that there's places where I need it. I need for cleanup. I need for, I'll use it for the programming. It's just useful for interfacing to the rest of the world through all the other idle ports. The chip itself does all of the floating gate programming. Yay. So nothing else in that part would be needed for any of that part of the computation. So there's a lot of pieces in here, including some signal DACs, some other memory map registers, and so on. And SRAM in here, which I always find funny when I look at the chip. This is the die photo of it. This is the fabric on this. Microprocessor is a little block here. But the next biggest element in here is basically the SRAM. And that's only 16K by 16 at SRAM. Granted, it's a 350 nanometer CMOS process, but I will tell you as we looked at this across smaller nodes, getting the same sort of compilation, that ratio will get even better for the most part. And so one of the first things you realize is memory is expensive. SRAM memory gets expensive on you.
It's the interconnect all the floating gates.
Yes, everything is floating gates in this chip. So all the way through the digital analog stuff, which is actually nice on the digital part because it really gets the leakage way down compared to typical FPGA.
But
so when I want to turn something off, it's like way off.
But you would still need a programmer to transistor to select the floating gates to program.
There is a whole programming infrastructure that allows me to say I can get to things. But for the most part, it looks, the programming infrastructure, when I go from program to run, it basically says, reconfigure everything. So there's a couple reconfigurable pieces where necessary, so that it looks like one big cross part of the chip. That was the architecture used here. Actually going forward, we'll probably actually do some sort of parts of those components all the way through. So that way it use more parallelization and some of these. Yes.
So if 2F is 350, what technology?
This is 350 nanometer.
If 2F is 350, what area is that little dot, not every dot that you have?
I'd have to go back and look for this chip. Certainly it's going to be bigger than 4F square, which is what you're going after. But
that's why you can make contest depending on the process.
Yeah, but it's probably in that range.
What things?
Yeah, it's probably in that range. But it's hard to get a lot of other, with all of the done at a system level, it's hard to get a lot of things to play that well. So that's kind of where this sits at the moment. But we can go definitely dig deeper into it if you're curious. And it also depends on which channel. So if we just kind of pull that and go, okay, so we know that that's there, or just examples. We can talk more about that. We do tend to be very focused when we look at these chips to talk about things that are end-to-end computing. So we're basically going from sensors to output. Basically it's important to solve the whole problem, not just say I'm going to solve a piece of the computation, and hope somebody put 3-4 FPGAs around it, and look, I have an answer. It's like, no, we want to be able to say if it's an acoustic system, I want actually a microphone through something that's a classified output. So we're very careful with that kind of approach. The nice thing with these FPGAs, because it can allow for heterogeneous kinds of structures, we can actually ask all about all in one device. So one of the multiple of all the early things we ended up building on this particular chip particularly, but there's a little history before it, was doing some of the acoustic classifiers, which basically be, okay, let's take basically a microphone input signal, bandpass filter banks. You might think of this as sort of a cochlear filter structure. These are C4 band filter banks, very, very efficient structures, just Q of 2. Roughly, we usually use 12 for this. I think there's 12 in there for some of the data side of that. Amplitude detect after that. We just kept these a single 25 hertz corner. There are different questions of how you choose what you're choosing here. But smooth it out. go that into a vector matrix, a multiplication winner take all block. It could actually use that to do a certain amount of word spotting kind of classification. It actually works fairly well. We actually ran this for a couple different blocks. And this was compiled in the chip, so we didn't do it as a tight structure. Numbers from 2016 were about 23 microwatts of power or less. Very unoptimized. In fact, we probably lost a lot of the power by being just kind of loose with the structure. But it worked, and that's the kind of structure you were talking about there. But it was kind of fun at the time because there was also a neuromorphic community a few years later, comparison on some of the digital structures, and it in fact did show per classification we were actually 1,000x better on efficiency. That was kind of nice. Sorry, I missed something. Sorry about that. Go ahead.
Yes, do you have the ability to do
Are you asking a question too?
Yeah.
Cool. Thank you. Okay.
do you have the ability to do a pre-outlet?
Yes.
So they're a separate block.
Yeah, in fact, there's a whole range of different, particularly for acoustic stuff, you have different kinds of preamps like watts. In fact, if you give me a raw MEMS microphone, that's my favorite, which normally it's hard to get your hands on. But if you can do that, there's actually some very effective capacitive sensing structure. Quite efficient when you can do that. Yep.
How do you train the vector matrix multiplication? You have like a digital simulation where you then optimize it with backprop or it.
Really good question, because we ended up initially building a first system to do the computation, but we eventually said, hey, we've got to figure out how to do a little training because at some point. And so we actually ended up building a whole training learning approach for how do you actually train these kinds of VMM winner take all structures. Now, the cool part of the VM winner take all is that in one layer, it's still a universal approximator. So in theory, I don't need two layers, like two neural network layers. I can do it in one. I might still use two layers. That's fine, but it works really well. And so that helps us start that. There's a whole learning technique that we actually, eventually put the whole learning structure on with using the processor and a few other things on the chip. Actually, but we're able to put the learning on the chip too, which was kind of fun because we didn't put any of the on-chip learning infrastructure we knew about. We just let's see what happens. We were not planning this at all when we fabbed this chip, trust. And so the learning algorithm, if you look at it closely, is an interesting hybrid between some learning algorithms that look like BQ kind of structures and LMS structures and other pieces. Get this right. And there's a long history on it. I'd be happy to talk about that. But yeah, we had to do something because the first one we did, we just hand dissed. No, we can't keep doing that. That's it's like, well, there must be a learning algorithm out there. And it turned out we found out not really. There's a couple bits and pieces okay, you need something we can really make in work and can fit into these structures.
I was going to ask the kind of related questions. What is the diarrhea of the whole die here?
That has a big die.
Problem? What is the like how many of your
Okay, yeah, two things. Yeah, so let me answer both questions. First question was, what's this die area? This die is a monster. It's 7 millimeters by 12. Big chip. Did I want it to be 12? No, but that's a long story I can explain on another day. Why 12 is annoying? Because most packages are only designed for 10. But anyways, discussion for another day. But there's a few things we complete actually didn't work, so we shut them off. So technically it would have been smaller had we done it right. But then the utilization for this classifier on this structure in terms of cabs, probably the utilization was probably about 10% of the cab combines, maybe, depending how you call it. It probably wasn't even that much. That was about the number of factors. Nice. Yeah, no, yeah, good question.
So the MST core is in the sleep mode and you're running the dust.
Yeah, when we're doing this, when we're just looking at the power part of it, that was just getting that off.
Because the MSP is itself 500 megawatts, like dude.
It's in this process, it's not an it takes some energy. But like anything in this process, I mean, it's a pretty efficient one for this process. But everything in this process will have some energy. And we can go exactly what the numbers are. Either that. Maybe one of the two of you. Oh, that's just you.
So I'm going to ask the naive question. Why as a
modest as do I care? This is a huge side. We're talking packages.
It depends on the problem you want to build. But it's certainly the energy efficiency helps. Every question knows, how tight and how many different dyes can you get in a certain space. Do I stack them? Do I do other things? It all depends on a lot of questions there.
So I meant by sure some modest.
Yeah, go ahead. You can ask them.
But I think some
Go you're next.
Yeah, I'm just curious, how much this will be changing you actually build the system so that it actually works well with certain data set? Like,
yeah. What data set? How many combines?
Yeah, so the first command word was only a couple of them when we first did the first set, but we found over time is that they actually use the same sort of architecture, and it was in the the 20 to 25 microwatt power level across all of them. And part of it, to be honest, is that most of I would say a quarter of that power was on the front end, and then this was like using way more power than it needed to by a long shot. So we needed a little more. It was really easy just to rescale it down.
do they have to scale out something to tackle a bigger data set?
At some point, yes.
So how will it be how big will it be? Because I can give the number or reduce that system to 1,000 words about the music one.
So yeah, if we're doing 1,000, if we're doing more of a custom system, it depends on which system we're putting in here. I don't think this chip would hold 1,000 word case in this chip, just because I don't think the capacity is it. Again, a configurable device on this. But there are cases where we've actually designed stuff at 1,000 word kind of numbers, and you get power. Trying to think, we haven't measured. What was the power estimates on that? I have to think about the power estimates on those. Yeah.
I'm just giving. I just checked them. I get 139 million 1,000 words. It's fine.
Okay, so who built that? Who built that?
Ready?
Who built that?
Price.
What is it?
Calcium.
Acid. Okay, and that's yielding. That's a good yield.
I'm going to fair comparison here with the
Okay, well, we'll talk about that one.
So we managed the thanks.
Yeah, no, I mean, we should talk more. No, but again, I think there's some good efficiency numbers as we look at that. Brett, I don't know if I got your question entirely. Did I answer it or not?
Yeah, no, I mean,
Okay.
it's kind of like
So for
how that price.
yeah, so I mean, the biggest reason that we didn't get a good comparison is that, like I said, we primarily did not program the VMM elements here efficiently. It was just like, oh, look, it worked. So every time we kept adding more stuff, it was like, still we never got near the efficiency edge of it. We actually think we actually did this carefully for the original set of problems. It's probably about a 4 to 5x lower actually than the efficient case, but everyone's like, yeah, good enough. Students let me go, we're done.
Good.
So that's kind of where so that's kind of where some of the numbers are. But even at that, it was actually fairly good what we're looking for here. And we should definitely talk about the scaling question. It's also fun. So once you get that, then we start, and again, there was a whole conversation. We did do the training. There was actually stuff where we actually did use the processor and loops. The training did actually take a bit more area, more power, because we actually had to get the processor running, as you mentioned. Thank you. But we're able to do this across a number of different cases. I'm just getting the machine learning stuff. We also did a bunch of other different problems in there. Nice linear reflection solvers on there, which has had its own set of discussions in terms of what the computing will give you. And, do other things. Also puts your random hot field networks and PDEs and all of these other kind of things in there. This is a hot field network for max cut, but we talk more about that if you're curious. And so there's a whole bunch of different problems in here that are possible. And then again, just partial list of stuff that we kind of have done into this chipset. One of the things that's interesting though, and again, I still showed all the computing stuff with all of the loading in elements. One of the things that's kind of fun out of this though is that all of these switches are not just raw switches, but this creates its own crossbar. And that turns out to actually change the way you handle when you do FPGA kind of, or like architectures because normally just the components and just the routing to connect to it. These components here actually say, well, wait a minute, I could actually use these for computing, which again, because every single switch here is a single floating gate element on the programming, which still isn't a computing aspect in the routing. That turns out to be really helpful because I could program these completely off, which means they're like below the power supply, or above the power supply, so they're way off, or I can turn them way on so they're below the power supply, so they're like as hard on as a transistor can go, or things in between in terms of the programming infrastructure. So we'll use that for a couple of things. You can imagine it is a crossbar, so I can certainly do things like, a vector matrix multiplication leading straight into the elements. So the elements look more like a boundary condition. But we'll use this to also say, hey, I need an extra voltage source here. You can pile that out. I need a resistor routing network for some reason. I can put that in there. A whole bunch of these other aspects are absolutely essential to how this works. To let you go, that's really cool. And we used it in the paper that we talked about, which switches are not dead weight. Along kind of sort of realize, wait, there's something to this kind of density of what you can do with this. The flip side is you go, wait, tools are going to be a real pain in the neck here because now it changes the tool question from how normal FPGA will look at this. And so I start getting a little more into system questions, some of the tool questions you get with the systems. And so the first thing is, so this is kind of like, again, picturing where the tool aspect is. Actually, everything sits in a virtual machine. We'll zoom into this more. Things are set up as blocks. You can actually still use that same structure to actually measure data. This is an output waveform from this. And all of that, this little board here, which is this little board here, is the entire chip sitting on there, running into this. So that kind of gives you the structure of this. First thing you might be asking is, so just curious, what is she measuring here? Because of the structure we've been using in classes for the last 10 years, more or less at Georgia Tech. And you can actually design the hardware separate, but you still might be going, yeah, but what is that circuit, by the way? Maybe you don't care. But it turned out this was actually an interesting little circuit. Probably could be a longer talk. People are curious about it, but at a short level, it's actually a bandpass filter that actually with an adaptive key with key rotation in the analog. So it's actually building a hot bifurcation infrastructure so where the Q and actually gets the human carry goes from 30 down to 1 based on sort of the core structure based on input amplitude. So it kind of gives you almost an AGC, which is really nice because it allows you then to go for small sounds, you get more gain. For loud sounds, it drops it down a bit. The core structure underneath actually looks like basically is a modification of what I would like to call the need second order section. It's a bandpass version of it. Those of you older time, you'd call this a classic second order section. Most people there was you go from the input here is low pass. Turns out you go with a cap input here, you can actually get the input of this. But it turns out you can turn this into a stable hot bifurcation. You actually read Carver's book on that whole discussion. He talks about some of the unstable properties, but with a little bit of cleverness on the floating gates, you can actually linearize these quite a bit and actually get a nice stable dynamic. You can get something that is a stable hot bifurcation, which then gives you a stable bandpass filter. So it's just a small little detail, kind of fun to build in this, but all this was completely all demonstrated on configurable device, which is kind of nice. So you're so actually go, I know the circuit concept. Let me just try this. And before you know it, you get experimental data. These, I think, are going to be a lot of fun going forward. But I figured people might appreciate it at least. Because these technically, now you can build banks this way. There's a whole bunch of other dynamics too. There's fun. So once you start there, you start to say, what does the tool infrastructure look like? And we tried out one tool for the simulation target design. And this is sort of all built in one virtual machine. It's kind of the core of this. It's all sitting, it's a Ubuntu VM, all sitting in Scilab and XCOS, to where, this was actually, to where there's actually a whole bunch of things like examples and other pieces in here. This is actually one example block that was at the time. And, but this is kind of how we think about how circuit blocks look. Like that was a Hashimoto's neuron block. I can actually take blocks here that are DC voltage blocks and they'll compile to very specific things. Actually, the output voltage here is going to be with 150 millivolts. Well, I want to gain that up to go into my ADC. So I'll just put a a gain block that gives me about 20, so good enough. And can run the ADC there. This is then this whole block. When you're done with this, you hit compile. You know, you can actually hit compile program, and you can actually run in measurement mode, and then actually this waveform, which is not the best tuned circuit, but it's a thing, right? And you can actually get all of this in one framework here. This is how we start thinking about design. In fact, particularly if I say I want a DC voltage block, I double click on it, I give it a value, you know, a couple digits precision, and it compiles straight down. It gets to be great fun when people look at this and they're like, wow, okay, so this is one way to think about how you deal with completely end-to-end analog design. What's also unclear is when you talk about this arbitrary waveform generator, this is partially using the processor. So that also had to be thought about. After the ramp ADC, data goes back into the processor.
Hey, so I think I may have asked you this years ago, but do you see the FPGA as being more route to design analog circuits and to test things, or do you see it as being an implementation fabric in itself? Because obviously, in order to do the reconfigurability, which may not be necessary for a lot of applications, you have a lot of infrastructure that you're having to support. Mm-hmm. And I just wonder how you see its sort of role in the that.
Yeah, so I think much like FPGAs, I think the answer is sort of yes. It's both. And the reasoning, clearly the prototype part is obvious. There's prototyping, you set to go design. You might get to the end of that, go, I have a design. Now what do I want to do? Do I, in a commercial sense, do I want to go and like build a commercial chip? And that has its costs and business questions. Or do I say, I've got an FPGA device. Why don't I just take this device and just keep stamping out the final solution on every single one of these chips and then just sell them as product? That's exactly what's done with FPGAs today. In fact, a sizable chunk of what was Xilinx and or Altera, which are acquired companies now, Intel, Still, and AMD, there's a sizable amount of actual revenue that comes from just stamping chips out for customers. There's a whole sort of ecosystem that's built around this.
But this is, I mean, it would seem to me, I'm just sort of thinking about it, that with FPGAs, presumably you're deciding that you don't really care as much about the power dissipation, you know, and so you're willing to have all that extra infrastructure. But if you're going for analog, then presumably the power is more important to you. So maybe you would want to take that step further to optimize and have a custom circuit once you know what circuit you need.
Yeah.
Does that make sense?
I think it does. And there's a question of what's the relative efficiencies between custom and configurable and so forth. Actually, that number on the analog on this stuff is actually pretty good. Probably the area one probably get more than the energy efficiency questions typically. But what you'll end up finding is it's an interesting question of how much does it cost when you do a full custom set chip. You know, so it's a business case that typically comes out. Well, it may just cost, may cost $1 million to do that versus I just have the chips now to stamp them and go. Yeah. So that's a dependence on volume and revenue and all sorts of other questions.
So what would be the kind of, what would you expect? I'm sorry to be talking. I hope these are relevant questions to other people, but what would you expect would be the difference, for instance? So between just stamping a particular design into one of these chips or making an optimal kind of version of that circuit on its own. I mean, are we talking about, it'd be half as efficient, 10 times as efficient?
I think it'll depend. It's a little bit depending, but sometimes those numbers tend to be. It really depends. It can go anywhere from 2x to 10x, and depending what that number is, will give you a lot of those answers. So it's not always obvious. As well as there's more I can say about that as I get a little further too.
There's a little bit of history about really conventional manufacturers like TI. TI for a while, so you have this chip that you look at it, but like modules, you can build switch card circuits and you can put it together and you can program them and you can put programmable devices and you can connect to circuits very quickly. And remember when, it's another device.
There's still one, two,
Well, I don't
couple of which you can buy, but yeah, no,
I mean, it's
there's an interesting issue, and part of the question is, and the simple answer, the biggest issue with that is if you're trying to build components that are going to primarily be used by analog circuit designers, you have a rough sell, because analog circuit designers tend to be a little bit more picky about some of these details. If you can get it to be big enough to work without a systems perspective, that people who are system designers can build it, that changes both the community and the ecosystem of which is using it. And I think the issue with some of the early chips like this, and you can still buy them at the Anodyne's, the obvious one, and it's a couple others. That's usually what their struggle is. How do you get it into a system mindset? What looks very much like an analog circuit constantly. And that's always been their struggle, and I can appreciate why they have that struggle.
yeah, I was at that point. If I have a device, and then send you a chip for the system level, that's going to take away a few like this, and they pretty better USB or you're done. Run, but it
Maybe. I mean, so maybe that's what you wanted to do, yes.
that's what they said now.
But no, I know.
But bunch.
I mean, if it works.
The question is where exactly is the analog advantage here?
Yes, what is the analog advantage?
So like the top bifurcation.
Yeah.
You guys
Yeah. What's the thing?
put it on a DSP takes a long.
Yeah. So in analog structures in general, a lot of the, particularly when things are still formatted in the differential equation kind of mindset, that's usually when it gets much, much harder. It depends on a number of these kinds of problems. As you can definitely get into it a little further. Typically, the more you lean towards the differential equation side, better on that. And there's some missing pieces there.
It seems to be very sort of outside. I'm not sure if that exists. Like on the decision side, people do timeout. Like so, you mean these surface where you use the fact that very fast slots, right? And if you open the analog side, if you try to put the entire system, like the differential equating system, into the chip in discrete components, right? It becomes big, right? If you trade in the area, but then you have something's potentially potential, but it's very fast, but maybe it's fast that it needs to be, or I don't know, like, or
you've mounted up the energy level that you need to tune down the biases as you need to. The nice thing about, again, starting with floating in elements is that bias current goes over as many orders as I need to. So you can program it to get hit an optimal point.
But it's some like a concept, like a theory where people use analog devices inside of the timeline, like weighted to map a big problem on a small chip.
It could be that the problem that you often find there is that you often have to you're spending a lot of time moving the data back and forth. And that moving data back and forth already causes a lot of cost. That may swamp everything else out. In fact, the interesting comment is when you start saying, well, these are all floating gate elements, you're like, well, actually the memory is right there. It's actually almost sufficient to have programmed it right there because I have to put the memory there or somewhere else. And so I can say, yeah, but that's I can make flash much smaller, but eventually you start to say these are all the same process nodes. When you start to make that argument, you're like, no, that you're going to go one place or the other. And you still want to minimize the amount of communication because that, of course, is the critical problem. So you can actually get quite a bit further on that if you want to.
So this makes the observation. If you're doing intercept landing and landing in that scenario, or you're driving around pedestrians, there is no such thing as processing faster than needing.
It's right down and maybe it's your R. I mean, I really like from
I said, I know it's a way to pick.
One thing said, I mean, it depends on all those latency, whatever. What?
I mean,
You just let them.
I see us, but
Yeah.
that's
What is that? I mean, well,
I think you want to.
if you want to do anything faster, burns more power, right? There's always but then the question is, what's the relative power between them? And that's where you should have to know the question.
Yes, if you're doing things in the antenna and you have a 5 gigahertz signal coming in and you want to be energy efficient and you want to do AI there,
Yeah.
I mean,
But
Yeah.
So I understand. And in that example, there may be multiple ones. So we'll leave.
Or if you want to do signal fuzzy at low frequency, for very low power.
Yeah, that's the other extreme.
Not sometimes.
That's let's see the other extreme.
Yeah.
But then you optimize your own circuits, but that actually much.
But it's the correct prototype.
Yeah.
Right. So,
And I think that's the question.
I can learn more in 5 minutes of playing with real physical circuit than in days of playing with spikes.
Yeah.
Those of us who fought spikes to trying to get the parameters in a reasonable way, reasonably accurate simulation. You still can't really trust that.
This spice will always converge.
Yeah.
No, well, not always actually. Not always. I do have counterexamples.
A system like this has a lot more parasitics, thought and inserting.
Yes, there's parasitics. Yeah. Although sometimes you can use those parasitics too.
Yeah, you could use.
There you go. So when most people look at all those tools, they don't realize underneath there's all this entire tool flow. There's a very detailed place around infrastructure to actually. So when you get these buttons, say program, it actually does compile. It does actually go from a high level structure down to an intermediate netlist level called LIF. Goes to the VPR, which we pulled from the FPGA community and hacked a whole bunch of stuff in there, and then get it down to actually running down on the device. So there's a whole lot in here to just get this in play. Even though you get a button and go, oh look, I can double click number and off I go. This has turned out to be really valuable, but it's not just enough. So this is sort of classically how most of the structures we have and where we use this. What we've been doing over the last couple of years, in a sense of it, is been modifying that tremendously to actually be able to go to a little bit higher level of representations. So I can start doing more high level synthesis out of this. Some of the representations are not just graphical that I can come in here, but also Python and come through this a modified version of this entire flow down through, gives me a switch list so I can charge in an FPA and put that onto this FPA or other FPAs with the right sort of technology file describing that FPA. You might also go, wait a minute, there's a different side to this flow that I forgot to tell you. And I did. But it also comes into this question of, I have a mixed signal structure from this high level. You can then say, take it from there, same concept that could go down into this side of the FPA, then can also go here and say, now I can actually have a whole flow that's taking some Verilog, taking a whole set of standard cell from the analog side of this as well, and actually come down towards a custom IC, which that actually is the 65 nanometer one, to actually say I can take this as standard cell and run it straight down. And this is actually some of the things that we're now starting to build a lot with in terms of saying, well, can I start building standard cell elements to both take this high level description and bring it all the way down. It's also a nice idea to say, if I want to make the next generation of these, I can start compiling those too. And so actually really leveraging the tool framework. And so much of that came from the fact of understanding we started to build this. And from all of this experience and some of the other things to go, there's a whole lot more we could generalize out of this.
Now, this may be a really dumb question, but would the FPAs that you're doing, would they be compatible with an approach like the Nego approach? And have you ever thought about kind of working together on that?
So the simple answer is, can we interconnect these with Nego and so forth? And the answer is, I think so. Have we talked about it? Yes, Terry. Thanks, Terry. I came in and verified. There's a lot of discussion, and part of the reason having this definition up here is it also allows us to have both either a text version or and a graphical version. But for a lot of the things, we want to start integrating this into other people's tool flow, we can start to do that. So there's a lot to that entire.
And then the question would become: is what Nengo is producing within your framework sort of efficient enough to make that relationship? Because I do know how that compiler level of things works, but
there's a lot to be said there. But I think it looks promising at this point for a lot of the ways some things are getting put together. I think you're next. Everybody else died.
So you have just a down compilation basically, but is there also kind of an upflow where you have to tune the circuits in a way to match your high level specification?
Yeah. So it turns out Because for the most part, the way we're actually lowering things down from high level to level, given the way we have some of the definitions, if I run from a high level, I can kind of handle that all the way down. So it actually still, that question about the programming accuracy, because I'm programming this, the accuracy still flows all the way down, and I don't have to necessarily come back up.
And this is for the standard cells that are obvious.
Yes.
So if I want to add a new one, I would have to figure out
Then we build that into
intermediate feedback loops. And
right. Then you have to everything we have is characterized when we do these. So you mentioned someone 65; those are characterized, and there's a couple more things to say about that in a moment. Yes.
I apologize in the patterns, but what I would find super interesting is like logs that have digital inputs and digital outputs and are analog in between, because there's some operation that is easier to do an analog. Right?
Sure.
This is if not that she just like essentially is a digital designing. Are you doing stuff like this in this log here? I mean, it's maybe not the most like the nicest orthodox way of doing analog stuff, but it would be very useful.
You certainly could do things, just to capture that question. So here, you can certainly do things where you have digital, where you could have some digital components controlling the analog piece in the middle and digital in the out. That certainly can be done. We certainly have done circuits like that over years. And so that certainly is a possibility that could actually be synthesized here, because there really is design of it, both meant to be not just analog coming through here, but also, it's meant to be mixed signal through there. So then it's possible.
I'm honestly thinking something like it wants to be operation like you have 100 inputs that will probably sum up and then compare this threshold value.
Yes.
I know, right? So I'm thinking about that actually, but maybe that's now.
No, I mean, yeah. You could probably, I think there are definitely ways to look at that. It honestly, at that point looks like a small, simple DMM plot where you just have digital in out and off you go. But yeah, you could definitely do, GMM with a threshold element, which does it for you, off you go. Now you might go, well, gee, it's only one midway. It's like, now I could have 10 midweights too if I wanted to. Like, okay, maybe you could do more with that. You're having flexibility there. Like almost every system you build, you have to deal with those questions. That's kind of the picture as I started looking at this a little bit further on. Actually, we talked about standard cells. We're not kidding about this at this point anymore. We actually have working 165, 130, 180, 28's of measurement right now. 350, we're finishing out, but we have a lot of history there. And so forth. And kind of building it such that all of these fit into the framework as we can build forward. Both to say I can target an existing FPA, I can build a custom device, can build new FPAs. This is where we're going. And some of this is already working. And as I can show you, these things are working. This one we're still finishing. But this is the game. How do we start to really bring a lot of the analog stuff into sort of the digital full synthesis mode, your top to bottom. And so then we can start getting into all sorts of things of what would new devices look like. That gets to be fun. And that's one of the reasons we care about the scaling question, because we really think there's a lot of opportunities to start building forward on these devices in terms of frequency, in terms of computing. So we get pretty excited about what's possible with these kinds of chips. And so that probably works out. I think at this point I've hit time, haven't I? How long do I have?
You're like 8 minutes over. But
Okay, so I should probably wrap about this one.
the next talk is starting in 20 minutes.
Well, I can wrap here, or I can quickly go through a couple things in 2 minutes, but let me just wrap here so I don't blow everyone. I think we've had such great conversation. We're really happy with this. So thanks everyone for comments and the conversation. And open up to other questions.
But I particularly want to report, hydrogen. Part
Hydrogen in
space.
space. So yeah, space is an interesting conversation, because you have to deal with things that are cold for the most part. You can heat them up. Ideal cold, which by the way, most of these, one thing I will say is floating gate set would behave well over temperature. We use a lot of, made them work well all the way down, including the FPAs all the way down to like 7 to 4 degrees Kelvin. So that's not a problem. The biggest question, so I think that would be very efficient. It'll be very useful because when you're in space, you don't want to actually touch it, that you can't. The biggest issue in space will primarily be the rat-hard questions. And it was very clear to me, floating gates will move. There's almost no good modeling under radiation for floating gates right now. That's something I'd like to see change. I might have more to say in the near future. But the reason I'm having the modeling is because then you can actually build strategies to take care of it. And I think that's actually quite doable, but you need to have the modeling before you can do that. Did I answer that?
It's
Useful.
Sorry.
I find this stuff very interesting. Like we're referring to the very high frequency stuff because it's a start of event related. So tools that we probably getting time it's on. Yeah, can you say something about those? Like,
Yeah, I could say a lot. So there was, the conversation on data point and how we look at this. How does, because we're at 350 nanometer, right? And everyone was like, well, how fast can I go with this? And the simple comment is, yeah, I mean, you can get like about 50, 60 megahertz through in that process node. But as I start scaling things down, 130, 40, so you have actually multiple data pieces and all of this. These open up different questions. For example, we're at 40 nanometer. We know that we can definitely get 4, 5, 6 gigahertz signals through there, versus without the 1 to 2, 3 dB loss through the path. And you can actually get that through the routing fabric, and we know that works. And so as soon as you can say, wait, I can actually put something from 0 to say 4 gigahertz to the routing fabric, that opens up a whole set of questions. Remember, we can also do the vector matrix multiplication in the routing fabric. So now the game gets rather fun in terms of what you could do there. That same tech concepts do work at the 350 nanometer case. At just the frequency level only goes so high, the density is only so high. By the way, if you're doing things where you want to do spatial temporal filters, you build ladder filter blocks and you do a couple of networks to get a flight. And we can talk about all of the computing architectures that we started to develop over time for that. But yeah, as you get higher and higher process node, you can definitely do some very, very interesting things. Obviously the computing numbers are interesting, but I actually particularly love the efficiency numbers of what you can do on what you could potentially do on single chip. And I can tell you exactly how to expect these numbers on an STA type of configurable device. But a lot of what buys us this is that we can actually do a lot of the computing through what is the routing infrastructure itself. And so that gives what you can. This gets really fun. That's 16 nanometer, 14 nanometer FinFET devices. It gets a lot of fun at that point.
yeah, but then the traditional CIM doesn't work. The CIM.
What do you mean?
That's the readouts. You have to worry about readouts. You have to make sure port you
And
have
all suddenly, what?
No, don't hold it. No. Wait, everything we're not doing. I don't know what you exactly mean by traditional CIM because I'm watching. So no, yes, you use these kind of switches. Obviously, I know where it came from originally because, yes, I know where the origin of it came from in 2001. But there's nothing in this conversation that says that's not possible. In fact, actually, those things do scale. The killer is if you're making just a block and saying I got to build a bunch of DACs and ADCs to make everything work. Well, I got an interesting DAC and ADC design problem, some of which I think there's some ways into that too. But that's not necessarily the way you want to build your architecture. Your way to architect your entire computing system. Because it's a block. It's a block in the system. It's not the system itself.
So it depends on what precision you're calculating that. So if you're calculating like 1 bit, if you're calculating 8 bits, then you have a speed with settling times that frequency.
Yeah, no, but the numbers are consistent. Interesting, the numbers are consistent out there.
And the job is not just gonna be post-power. You're gonna build coaxial structure. For those who are building things at that frequency, let's build coaxial structures for every wire that's your density goes down to.
You have to be very careful about how you shield your line. Yes, there's design techniques. There's no question about that, Andreas. But I'm also not ignoring them in my comments.
I don't think you're making the argument. I don't think I'm making the argument. I don't know that you guys doesn't make sense. It makes absolute sense. the argument that I'm making, whether FPAA is like 5 gigahertz makes sense. And I think that's a question at hand.
Okay.
I mean, that's,
But I would argue yes, and you seem to want to.
I do know,
So fine, we can have this argument. We can take this offline as well.
every year.
Yeah, and but the goalposts keep moving every year because things keep getting achieved.
Yeah.
Yes.
I know.
Come on, Andreas. 30 years of this. Come on.
Okay.
Okay.
But I have a question relating to Mike's question, which was you said again, and it's a naive question. You said that the FTAs worked at very low temperatures.
Yes.
And I wondered what if you were going from high temperatures to low temperatures, like
Yes.
going up into
Back and forth.
yeah. What does that do both from the I mean, does that have any different effect on an analog chip than it would on a digital chip? And also, is the behavior different? So if you're fluctuating between different temperature ranges, maybe because you're closer to the sun or further away or point to the sun, does that matter?
So there is some. I mean, there are design styles that are more temperature sensitive than others. So you could say a program will run over 40 degrees C, 100 degrees C kind of ranges and so forth. There's some pieces that work better than others. There's also a question of a stress test of, say, a program at a room temperature and I drop it down to 4 Kelvin and I bring it back up, you did something challenge with the charge and that direction is not going to be a problem. That you've done multiple times and it looks fine. So I would, and that's not shocking because most CMOS chips are designed to be able to handle that. So this has a lot to do with sort of the insulator and the insulator interfaces and so forth. So that'd be surprising if that got in big trouble. But yeah, design over temperature is like the big issue a lot of analog circuit designers always worry about. And I think the thing I would say about it is that we didn't, if you look at analog design, there's really only one thing that's ever designed well is temperature. It's called a band gap. Thank you, Diana Spitis, for putting that in this PhD work, and everyone copies the same derivation. Basically all the way through. And there's a couple other things, but there's a very, very few. And one of the things we started to realize by doing this is how to actually, because everyone would ask us, but how do you make something that's programmable and temperature insensitive? And so we had to learn how to do that over time. And that actually led us down the question of, hey, how do you design circuits for particular temperature dependencies and particular approaches? And so we spent a lot of time actually looking at those questions because after all, we were able to deal with a lot of the other questions. This one came straight up. So how do we think about it? It was an opportunity to really think through that design space. So I wouldn't say it's everything is perfect always, but there's a lot of good techniques that work depending on what your specs are. That's probably as good as or better than most industrial analog kind of design. Again, good question. Yes.
I know last year that made like various analog kind of computational systems, usually from what I've seen tend to avoid floating gates, and in other techniques they have all kinds of problems, right?
Right.
Do you think FTAAs are kind of a solution to those problems, or just floating gate structures in general? I guess I'm kind of wondering why don't they see kind of like competing works, like competing against defects, IRANs, or even just CMOS devices with floating gate structures that do the same kind of computational.
Sure. There was a lot of good questions in there. Let me see if I can get some of them and then tell me which I missed.
Sounds good.
So is the FTA a way that will work with a lot of the floating gate stuff? I think in one answer, yes, because I think it's a way that hopefully these become widely available, which is something I don't want to happen. Only so much I can say at the moment, but if it is, then anyone can pick one of these up and go, oh, look, I can build these things. And so I don't even have to worry about waiting for someone to try to fab my mistress and hope it works, and whatever else happens there. So I think that's the case. I do think the floating gates and the floating universe have been very robust over the years. And in some sense, a lot of the early crossbar conversations were more than 20 years ago now. And most of this was all beaten up pretty well 20 years ago. And so now the question is, okay, it's there. maybe the different question would be is, well, why do people not use this versus other techniques? And that's an interesting question. I think is less technical and probably has other things in the middle of it. It's a question I do ask myself often because most of the, I would still argue for any of the crossbar things that are built, the floating gate approach is still outruns anything else by a long shot in every metric that I know of. So slightly confusing from my perspective, but I also know it's arguably is not a real technical, but radiation hardness is an interesting question. We can talk about that, but for the most part, that's what I end up seeing. So it's a confusing question a little bit of what's going on. And I would love to hear other people's feedback if there's a reason, because I'd be happy to, I'd like to learn.
Next, people done real apples to apples comparisons of just taking the exact same circuit, doing it with floating gates, with RM, with speeds, like it's actually possible, right?
Oh, it's very possible. It's very, very possible. And I don't know of any explicit apples to apples comparison where you say, we put floating gates on IC process, where let's say I also have resistors on that same process, and then we put both of them on the same process and do an exact comparison. That'd be, I think, closest to apples.
And so my kind of question would be, I'm curious.
And by the way, I'd love to do what I just said.
RRAM, crossbar arrays, like stuff of CMOS, like kind of SRAM or DRAM cells. At least I don't know of any kind of dedicated circuits that are floating gate crossbars with like results. I'm not sure if you have anything like that.
There's actually quite a lot of floating gate alphas and results going back easily 25, 30 years.
I think it's just a matter of people ignoring those results, or is there some kind of catch there that people are, I don't know.
I don't see the catch. So it's an interesting question how you interpret that.
It's just like nobody ever got in trouble for buying IBMs, but they get in trouble for using GH circuits and taking out the analog research.
It's an interesting question. Yeah. Happy to talk more about it. I'd love to understand, but like I said, if we could actually do something that's like, here's a bunch of things on the same IC process and do a direct comparison, that'd be wonderful. I'd be all in for that.
So, but what would you compare?
If you said, hey, just said initial comment was, let's make it crossbar across all of these things.
So programmability, people have compared, like how effectively it fits. But in terms of readout, I don't think you can be plotting it. I mean, that's fundamentally the subject algorithms.
Putting it, just fun.
No, you said he doesn't think you can beat them.
Yeah, you can't beat them. I don't think the
Programs are programmable transition.
Yeah. So, but you could also argue, what's the area size? What's the other thing? You could compare all the other metrics and just say, like, here's what I have.
So,
Dominant. And
what's eventually floating gate is flash. And flash has come along with the density of flash.
Yeah, flash, yes. Yeah, it's incredible what's possible. I completely agree with you. So I can certainly make all the conversations. Say, here's how I see the comparison. But it was college like, hey, so what do you do an apples to apples comparison? You just put them on. By far, the best apples to apples comparison would be just put everything on the same IC process. And again, if it isn't on a commercial IC process, it's probably not real. So we're just gonna ignore that and compare. It isn't. And that seems perfectly fair to go, that's like what numbers are.
I have to say, let's stop it. I get frustrated that there isn't some agency like NIST or something whose only job is to say, we're not going to take what Jen wants to do or what these people want, these membership folks want to do, but we're just going to compare them agnostically. Because I think the problem is that anyone who tries to do this is going to be accused of bias.
Yeah.
And I think it's a really good idea to do it.
I think it'd be a wonderful thing to have somebody who's agnostic to this whole thing. Maybe they could talk to people to just make sure they're getting the right techniques. Let them build, let them compare. I would love to see that.
Yeah, from non-experts, people switching paraplate versus technologies. Yeah, it is very frustrating because the comparisons that we can do is here is a commercial slash in a whatever custom process that they have that was super dense, right? Has great numbers. here was a completely different cross structure that someone building university process and it's red energy numbers. There's no way of comparing them. And as soon as you try to use one of that, it's like, oh, these are only available as like megabyte macros. You cannot use
Right. Exactly.
these have the problem that they have this crazy support structure around. These need 9 volts plus minus or whatever. And it's like one of these weird features that if you try to build the same circuit on all of them, you have no idea on like, oh, what I have to pick out.
I think that I absolutely agree with you that you really want to be able to have something all over, something that you can compare against equally. I do think that you'd have to say everything on that comparison better reach commercial process. You shouldn't think it's only gets fair, because if it hasn't got at least that level, then okay, now it's way too speculative coming in.
It's also a question of access, right? So ideally, you want a 3D NAND. That's the highest density of memory that you can get.
That would be beautiful, but no one's going to give you. But just even saying planar CMOS or confess CMOS if you wish. But let's say planar CMOS, if it's available across the different things, just compare that. That seems fairly apples to apples to start with. And let's see what you get. That would seem to me, and by the way, if anyone want to do that or somebody is wanting to be an agnostic person to put all this together, I'd be very supportive and it was telling you.
Has this Optima program.
Yes,
But the main thing is, do you know folks who have access to the high technology? They can propose many of these high efficient CIM structures.
Yeah, Optima is an interesting program. But then I'll let that sit on it. I see. Ideally, that's what that program could have been. Yeah, let's get some
Apples comparison. Everyone is then building a full system analog, and then people like, how do you then compare it? So, like maybe some people build a stupid architecture. You're showing because it's proprietary. That's the short. And that's why I'm saying that, for example, we are now building that structures really about results. I want people to put the same structure on there for the floating edge, for example. And I'm not sure you have to do to actually do that, sure, but that's sort of instruction. Shouldn't be too hard. And you can do a bunch of different architecture, like elements, and some of them will favor some technologies, others will favor other technologies. Right? I mean, if you need super high density something in here, DRAM wins by not, but I don't know, maybe able to get them process.
I mean, it's really a good question, and I'll like I said, honestly, I'd be open with conversation. I'd love to see it happen. I'd just love to see it happen.
Take that.
Thank you for joining today. My name is Jason. I'm a grad student at Harvard, and today I'm joined by Benedetto online. And together we will present to you the NeuroBench project, as well as a novel model L2MU. All right, so starting on the NeuroBench, you'll see this logo a lot. We just finished this logo, and I'm quite proud of it. So NeuroBench, this is a community-driven benchmark framework, in part with the contribution of very, very many representatives across the neuromorphic research field. So let's start off with some definitions. First off, a benchmark. This is a standard for measuring performance. You all know what a benchmark is, and more than likely you have run your own benchmarks. In athletic terms, this would be something like the standard size of a track and field. Right? We can't have this thing changing shape, changing size, or else nothing will mean anything anymore. The benchmark is a standard. Next, benchmarking. Benchmarking is running benchmarks to compare different solutions. So this can be something like a race. Here, the solutions, or in engineering, so I'll call them solutions, but in our athletic terminology, these would be like the runners. And the runners are going to complete the same task of running around the track, and that would be benchmarking. And finally, a benchmarking framework. This is systematic benchmarking and implementation of novel benchmarks. A benchmark framework, in the athletic terms, could be something like the Olympic Federation. The Olympic Federation includes standards, those are the benchmarks, for different types of sports. And as you all know, the Olympics grows every time, new sports all the time, novel benchmarks are introduced. Right, so novel benchmarks such as, I don't know, skateboarding, now that's in the Olympics. All right. So benchmarking, I'm gonna make this first very big point. Benchmarking under a common framework, and now we're talking about research, aligns research identifies best practices, and drives technological progress. So imagine if we didn't have something like the Olympics and everybody was just out here claiming that they had the best 400-meter run. You know, we're not going to get technological progress like that, where technological progress could look like figuring out how to minimize air resistance or developing the best shoe technology, things like this. All right, benchmarking under a common framework does these great things. And now I present NeuroBench, a benchmark framework for neuromorphic computing. NeuroBench has 3 goals, to be inclusive, to be actionable, and to be iterative. First off, on inclusive, we would like that NeuroBench is community-driven and makes minimal assumptions of the solutions. So in a budding field with diverse research features, we really need to be inclusive of all these different types of solutions. Next, actionable. We cannot have a benchmark framework if you can't go out and implement the benchmark, right? So actionable requires that there is common tooling associated with the benchmarks. It's portable, it's standardized, it's documented well, you know how to follow NeuroBench. And finally, iterative. Benchmarking efforts have come up before, but often they might fail because the promise is too large. So NeuroBench aims to deliver, provide a starting point, and evolve over time. All right. NeuroBench contains 2 tracks. There is the algorithm track and the system track. This is because neuromorphic hardware is not fully mature, and oftentimes a lot of neuromorphic research will work on platforms which are not considered neuromorphic. So we're going to be able to benchmark algorithms where we have hardware agnostic measurement. Hardware agnostic in the sense that it doesn't matter what platform you're running on, the measurement will be the same. You're on a GPU, it takes you some amount of time, your measurement will be the same. If you're on a CPU and it takes you 10 times longer, your measurement is still the same. We're going to be measuring complexity here. Right? And on the system track, this is where we are actually benchmarking hardware. So this is for deployed performance and efficiency measurements. All right? And there is this natural distinction between the two, algorithm track and system track, at least to start, where the algorithm track is more associated with these research and large scale or complex tasks. And meanwhile, the system track is associated with applications or commercial use cases. NeuroBench has 6 novel benchmarks as part of our initial iteration, and these are on the algorithm track, few-shot continual learning with different keywords, object detection with event cameras. This is a giant data set. Motor prediction of a primate, so given neural recordings of a primate, predicts the velocity of its fingertip. And finally, Mackey-Glass chaotic function prediction, which you've seen before in this workshop. That's on the algorithm track, and I remind you that there is this natural distinction where a lot of these tasks are research or large scale, and many of them just don't map well to existing neuromorphic hardware now. On the system track, we have tasks around somewhat commercial use cases. So we have an audio task, which is in acoustic scene classification. This is essentially just the same as keyword spotting, except your audio data is from environments. And then we have, of course, QO, the optimization problem.
Can I ask about the qualifying part of the Olympics? Like what quantifies as neuromorphic? A lot of people who work on GPU algorithms also say
Great question. Great question. Nothing quantifies as neuromorphic. We do not make any definitions of anything. So we're not defining the term, but we are saying, if you consider your work neuromorphic and you'd like to contribute to the benchmark framework, we invite you. And this is how it's been community driven. We have not defined neuromorphic in any way, but we have developed a benchmark framework that is reasonable to people who consider their work neuromorphic. All right. Any other questions so far?
And it's good too, because that means if you're not neuromorphic, you can say, well, and I can beat these neuromorphic technologies at their own game if they choose to, right?
That's
So
right.
it's yeah, you need to be that inclusive.
That's right.
Because also the reason being like NIST generally runs some of these benchmarks for a different set of tasks, right? So is there a specific intent here to say that, okay, we are going to create our own set of tasks and hopefully that gets a wider adoption, or is it,
Yes,
okay?
yes.
I think isn't the point, I mean, not to put words in your mouth, but the point is that there are lots of tasks that have no benchmarks because the existing technology is not good at them. And therefore we're in this kind of double bind that we have no way to prove that we're good at things, that there are no benchmarks to prove that we're good at them. So it's a sort of a vicious circle. Although I still don't like the ones you've chosen for the system track, but that's
Oh,
my
okay.
own prejudice.
And I will say that nothing here is my opinion. These are opinions that come out of the community.
No,
And I'll present them. I'll present them to you, echoing like as the voice of the community.
I have to say, Jason really ran a lot of meetings with lots of people, and this is kind of
With lots of arguments.
and lots of arguments.
We were very patient with some of this, with these cards.
Just because I don't like something doesn't mean it's not good.
Then you can chat more and I can voice more community opinions to you. Alright.
So, Jason, maybe you can draw an analogy from the tiny ML community, which there's things like this.
Yes.
And so, again, it's basically an open framework.
It's an open framework, and I'd like to present some components of that open framework for you. So I'll take more questions later, but okay, let's get into system benchmarking. And I wanted to hit this one first because this is the most under development. Benchmarking hardware is extremely hard. So there's not much to present here, but I will show you. In terms of challenges on system benchmarking, in this space, we have a wide variety of hardware architectures, mixed signal designs, digital designs. There's no architectural standard as of right now. And that makes it difficult to standardize what types of tasks and what types of measurements you're going to pull at. And of course, also many designs are in non-commercial ready dev boards or only synthesis. My advisor runs machine learning, the machine learning version of this called MLPerf for machine learning systems. And in that case, they're literally trying to sell you their accelerator, their GPU, which is full software stack, and you know exactly how to get a model and put it on there, right? And because of the maturity of that type of hardware, they have an easier time building standards, building a benchmark. In our space, this is more of a challenge as we don't have that type of maturity in the hardware.
And also it's likely that at some point, it's gonna be a proliferation of specialized architecture, which are gonna be good for one task and nobody else will be able to do it.
Sure.
I mean,
That's kind of the goal, right? You want a neuromorphic.
well, I don't know if this is the goal for the system.
We can talk about how
Yes.
this might align, but I'll provide you our approach, and this is our first iteration approach. For the system benchmarking, standard application level benchmarks, application level meaning they're very high level, solve this task. And it's not something low level like how much did a synaptic operation cost you in energy. Standard documentation protocol. We don't have the engineering strength in order to try to develop a completely consistent engineering, measurement in every single hardware platform we want to benchmark. Our approach then is everyone writes what you have done in a way that is standardized, in a way that is transparent. And based on this, we'll be able to move towards further consistency in the next generation designs. All right, like I said, there's very little to present on the system track. This is our approach right now.
So Jason, is the goal like having a venue like Telluride host some of these competitions, or?
Yes, that would be great.
Okay.
That would be great. Once we are able to develop the first initial results and we have a framework set up, it would be amazing if we could have events like Telluride, which once a year collect new results. All right, today's focus, I want to be hands-on with the algorithm track tool, and we can chat more about system benchmarking afterwards. So is there any quick questions about system benchmarking?
Well, the elephant in the room is data sets.
Data sets, okay.
I mean, you haven't said anything about that.
I haven't, and not yet.
Okay.
All right. Now I'll get into the algorithm track harness. This is our tool for the algorithm track. And I forgot to put in a slide to remind you again that the algorithm track is for hardware agnostic complexity measurement. The algorithm track harness is a tool for automatic benchmarking for all types of neural network models. It includes data sets, data processing, and various metrics, all in its infrastructure. Currently, it's compatible with PyTorch-based libraries, of which there are many in this community. And it is actively maintained and built for extensibility. Stonks only go up.
Sorry, for those of us who don't get the joke, what does that mean?
So this guy believes stonks only go up, and that guy's me.
It's only going to grow.
I'm sorry, this is very Gen Z.
Okay, sorry.
Okay, I'm sorry.
My daughter would get that joke. Okay.
Actively maintained, I would say, by people like me and by people like Benedetto, who is going to do the second half of this talk. We have he has in particular has contributed very much to this tool, the algorithm track harness, and we have built it in such a way, always thinking about how it can be easy to get on board with and also extend yourself. Yes, and with this tool, we hope to move to standardized algorithmic benchmarking. All right, so now I'm going to present to you the metrics. So like I said, the algorithm track measures complexity of your neural network looking models. And that's divided into two things. I'm sorry, first, so no implements of the runtime platform, just to remind you. So we have complexity divided into two things. There are static metrics and there are workload metrics, where static means that no data needs to pass through. This is just a feature or a metric measurement of the model. And workload means as we pass data through, we're going to be collecting this metric. So of course, the easiest static metric is footprint. Footprints, you can compare it to deep learning, where in deep learning, you have something simple like parameter count. Okay, anyway. The next is connection sparsity. So based on your synapses, how sparse are your synapses and connections across the whole of the model. And the next one is execution rate. This is actually a feature and not measured. So this execution rate, I'll give you an example. Say we have this primate reaching task, which is taking neural data and then trying to predict the velocity of the fingertip. You can do this at something like 1 hertz, once per second, which would be probably really bad. You can do this at 1,000,000 hertz, which would probably be really, really bad when you try to deploy it to hardware, probably impossible. Or you could do it at something like 25 hertz. All right, so this is what we mean by execution rate.
Do you want questions for these metrics now or later?
Now it's good, now it's good.
Footprint, what does that entail exactly?
So footprint entails the size of the model when it is to be deployed. So this can take into things like number of parameters, quantization of those parameters,
Right. Okay.
and so on.
Yeah. Is that not very closely connected to connection sparsity also?
Connection sparsity.
I mean, do they not overlap?
I guess they can, but it's very helpful to be able to measure your connection sparsity. And if you just had this footprint number, it's very difficult to, it might be very difficult to say how much better is my model.
So one is really has to do with memory, the other has to do with communications, essentially.
Sure.
What is effectively the cost of communication? Is the connection sparsity?
Sure.
So why not take some of the metrics from MLPerf? Some of the metrics there are standardized.
Oh, we have.
Can't those be?
This is on system benchmarking, but yes, we have. And there's many issues we run into with that, which I can tell you about afterwards. All right, so on workload metrics, we move into accuracy. This is the easy one. This is how well did you solve the task. Activation sparsity. So if you have these neurons, how many, what is the sparsity of their activations? In ANNs, this might be something like 0. Or if you consider ReLU, when ReLU outputs a 0 as activation sparse, then that could be that. And of course, in the spiking network, if you don't have a spike, that is the absence of an activation.
Jason, just-
complex, like what the wiki can do.
I'll get into that point right after this.
So Jason mentioned like interpretability. Where does that come in? Like how do you, like is the model interpretable?
Oh, I think I can answer that question on the next slide.
Okay.
Okay, then we have synaptic operations. Synaptic operations you can think of as the cross between connection sparsity and activation sparsity. However, it's not a simple cross because oftentimes you might have activations which have a different type of fan out. So if you have very unstructured pruning, you cannot just simply multiply these two. This is the reasoning for having a synaptic operations metric. All right. So like I said, the algorithm track metrics measures solution complexity, and this can give intuition towards deployed performance. Our hope is that taking a look at these metrics, you might be able to say, how will this be effective when deployed onto some type of hardware?
One question here. I'm a bit surprised because like complexity in the traditional sense is less about like numbers that are like a number that you measure. It's more about like scaling laws and so on, right? Because they like in algorithmic complexity theory, people are not thinking about like, I mean,
Sure.
things can change. It can be a constant, but
Sure. What might be a better word than complexity?
no, I don't know. So I was more wondering in the other direction, like, wouldn't that also be like an important thing to consider, like an algorithm here, like how it scales?
Yeah, you know, someone said that exact same thing or something very, very similar at NICE a couple months ago.
It wasn't me, but
It wasn't you, but yeah, I think that would be a great idea. And also, yeah, so some of these words, I don't like them a lot, like workload metrics. That feels like an awkward word, but I couldn't come up with anything better. Yes,
dynamic,
dynamic.
static metrics, dynamic metrics.
Yeah, honestly, that's not a bad one.
One thing that's misleading about this connection sparsity is that unless the sparsity is balanced, it becomes really awkward to distribute it across different clustering elements.
Right.
So you need some metric of connection entropy or connection structure. I don't know what that metric would be, but for example, if you measure the entropy of the number of connections. In other words, very low entropy means that all the, you have a few connections with lots of weights and many connections with very few weights.
Yes.
That's really bad.
Yes.
What you want are all the connections to have the same number of weights, in other words, have high entropy.
Yes. That's a great idea.
Yeah.
I'm not going to claim these metrics are perfect. There are issues with them, such as, the particular way we implement them as well. Is probably not perfect, especially in a general sense for your model. But I wanted to present the next slide, which is our harness, our framework is extendable. So the defined metrics, these measure general complexity and minimize assumptions about the solution. So if you're passing in something that looks like a neural network, we'd like that these metrics apply. However, more specific metrics can be defined and easily integrated into our harness infrastructure, including things like neuron dynamics. If you have a particular neuron model, you can say this is the cost of dynamics measured at some frequency. Robustness of your model, fan out of your maximum fan out across your entire network. You might want some of this to see if it's even possible to deploy. Question?
So who vets that then? So if you're the Olympic committee, who's vetting this new sport that I just made up that I'm bringing into my field against?
Let me see where I have the slides for that.
150 one-legged hawk that I'm really good at doing actually. So
I have a slide on this, it's towards the end, but essentially what I'd like to say is the community builds this framework. If you have a good idea, you should put it in and you should say, here's our open implementation of this metric. We believe it's a good idea because, and then people will use it. Yes.
You're gonna get more into detail what it means to implement it.
Yes, that is the next thing. Yes.
No, I mean, I think you haven't told us about end-to-end solution yet. And so I don't.
Oh, what do you mean by that?
I mean, you're solving a problem with an algorithm. And so we haven't talked about the problem or the data set.
I showed you 4 tasks as part of the algorithm track.
Yeah, I see. So they refer to those.
These and any other algorithm task you can think of. It's a framework. Yes.
I actually think Paul's point was a really good one in the sense that, like, regardless of what gets added, right? In terms of if Paul invents a benchmark, you always have the danger that people are going to ignore benchmarks that they know that they're not going to do well in, or that they indeed have not done well in, and are not going to publish those results. Because that happens, for instance, in the pharmaceutical industry all the time. You just, push aside things that aren't convenient. So the question might be, is there some way that as a community, you can say, we would expect if you are publishing a paper, which, that's on an algorithm with these kinds of properties, that you will have gone through and presented these benchmarks for better or for worse. That if you had a kind of discipline to it, and that your paper was not going to be accepted if you didn't at least bother to use the standard benchmarks, maybe that would be a way. You're looking skeptical, Terry, I don't know.
But because the tasks are limited. There's 4 tasks, anybody can create any task they want.
We don't need to have something as stringent as if you don't comply to NeuroBench, we will not accept your paper at this point.
That's also and every perf has like open and closed settings, right? Like,
sure. At this point, this is a starting point. We are moving towards standardization. We haven't reached standardization, and no one knows when we will. But here's a step. Here's a step forward. We have this.
It's only just a level of skepticism. Like, it's like, oh yeah, that guy submitted a paper and he didn't bother to use any of the standard benchmarks, probably because he was going to fail them. Then that would be a level of skepticism that you could write as part of your review of that paper. I'm just saying that it could be used in that way.
Sure, this is a comment mostly to the audience.
Yeah.
Question?
Just for context, I guess first, what is MLPerf, and secondly, like, is the idea that if people say publish a paper with the results relevant to the benchmark, that you would like host it on a website?
Yes.
Okay.
Yes, there will be some type of leaderboard. If you say we did this well with the NeuroBench harness and NeuroBench defined metrics, we'll put that up. And this is the part I was getting at earlier with tracking development and identifying the most successful features. This type of leaderboarding. All right. I have not very much time, and I'd like to give time that we will present you work through the benchmark. So I'm going to move quickly through the next slides, which will be more of a tutorial hands-on of what the algorithm track harness looks like. The algorithm track harness, you can pip install. I'm very proud that we have developed to this point. It was a lot of work, and you can find it here on GitHub at NeuroBench. So at a high level, we have the top benchmark. The benchmark is going to take different objects which represent your task and your solution and call this run function, which will just automatically give you your metric results. All of these components have standard interfaces and can be customized. We built them to be customized. First, model. This is a wrapper around your trained neural network, includes boilerplate inference code, and different hook management for the metrics. We have 3 so far. The most standard, abstract class NeuroBench model, torch models. So this is anything built in torch, wrap it in a torch model. It'll work to the extent that we've built it to work. And SNN torch models for the particular framework.
And again, this doesn't need to be spiked in neural networks or anything.
No.
I can take a microcontroller and run my algorithm.
Yes.
It's not for hardware, though, it's for algorithms.
Yes, it does not matter what platform you're running on. If it is capable of running the Python code, then you will get the exact same numbers.
It's not a hardware benchmark, it's an algorithm benchmark, it's an ops benchmark. Oh, you understand, Andres? At this point, it's not a hardware benchmark.
I'm presenting to you the algorithm tracker.
Okay, yeah.
Next, the data loaders.
intent on that we're gonna get static metrics.
There we are. Next, the data loader. So this loads our evaluation data. It has the same interface as the very standard Torch data loader. So therefore, it can be used with other Torch data libraries, such as Tonic from Gregor. Data sets for all of the NeuroBench tasks are available, including these 4 plus more. And these tasks, we include novel data sets that we have collected or published as part of this B 1.0 of this project. So this includes a Mackie Glass time series for the chaotic function prediction task, as well as a continual learning data set with very long multilingual keywords. We have preprocessors and postprocessors. Preprocessors will apply to your data, so example, downsample encoding. Postprocessors will apply to the network output, so for example, if you're counting your spikes. And finally,
And so the preprocessor are not included, the preprocessing is not included in the benchmark.
yes, we do. We currently do not measure preprocessing in the benchmark.
Which may be one of the biggest things.
And this is something that can change.
So for acoustic, for example, is everything.
I'm not going to hear this argument now. I have a presentation to do. Metrics. Metrics. So here, static metrics are calculated without any workload. So for example, the footprints. And workload metrics use the model output. So for example, accuracy. Or they attach hooks for runtime tracking. So this can be the activation sparsity or the synaptic operations.
What does that mean, attach hooks? What do you mean?
So essentially in PyTorch, the way that your model is constructed is in these module blocks. You can attach hooks to each module, which is going to extract features of that block during runtime. And say you can extract something like how many spikes did I do at this time step?
Connectivity, the links.
Yeah.
The metrics.
Sure, it's like a callback.
That's okay.
All right. And right now, this is very PyTorch specific, and all of our implementation is very PyTorch specific. But you can see how the top level is very general, and we've just, made these blocks, and you can fill in the blocks however you'd like.
But aren't you constraining the community to using those only operations? How about dendritic operations? Like, would that become part of this?
Do you see a problem in how this is defined that wouldn't allow me to?
So in terms of bench, because you're taking activation sparsity and synaptic ops.
I had a slide back here saying it's easy to add your own metrics.
No, but I may be using some dendritic computation, but they may not be counted as synaptic ops.
Yes.
So I have these.
Yes. Then you must customize the metric in order to get a reasonable output. And there's no way we could write the framework for your tailored solution.
But I thought
there are too many tailored solutions.
So
like I said, we are taking one step at a time towards standardization. At this point, we have this many frameworks, which are part of it. And I'll have a slide on this later as well. I'll get there. All right, so I want to say on metrics, you can swap them in and out, and the metrics calculations may significantly affect runtime. So therefore, from this top level, if you were just to pull out different metrics, that can affect how fast your run goes. And it's as simple as just changing this line.
So how mature is your ability to parse through static sparsity, for example, at the moment? I asked that because a lot of models are moving towards using things like Triton, and there's a bunch of weird things that are integrated with PyTorch, but are not PyTorch.
What's the question? I can't hear you, Jason, sorry.
So I think the question is on the maturity of the framework for a very particular case of static sparsity. I don't know. I would need to have a look at what the code looks like, but if you can imagine that it fits in this, it will probably be able to fit in there. All right, we have examples built up. Also, these examples are our baselines for each of our novel tasks in spiking neural networks, normal ANN convolutional neural networks, LSTM, echo state network, and a continual learning example. And those are all available at this link from the repo through the examples folder. And I will specifically point out these two as non-trivial benchmarking tasks. The continual learning one, which has to include continual learning steps between different benchmark sessions, and the event camera object detection, which is using a very large data set, as well as a different model head for attaching to the network to output the boxes. And yeah, so we have examples of non-trivial benchmarking. All right. In addition to the 4 V1.0 tasks that I had mentioned, we also have examples for Google speech commands, DBS gesture, and this new IMU activity recognition task, which Benedetto will talk a little bit more about. What I'm trying to get at with this slide is it's been done and it can be done for your type of task as well.
And data set.
And data set, yes.
But why not just choose just one or two, like for continual learning, there is a final metric, right, in terms of accuracy, performance, rather than those other heuristic things, like neuronal dynamics, I don't know how you will compare the performance of neuronal.
And you wouldn't. If it doesn't make sense to benchmark, then don't. So for example, in some cases, it may not make sense that activation sparsity is measured in some way for an ANN and in some way for an SNN. Like that, the metrics are there for your use. They're your building tools. Like I said, these are not full standards yet. We're moving towards standardization.
So the performance is how well you do in accuracy, let's say, and the other metrics is really what is the cost of attaining that performance.
That's right.
That accuracy.
Yes.
Andreas, stop, sorry, don't get me going on it.
Yeah. What?
Performance is not equal to accuracy.
Performance, all right.
Annoying.
Okay.
Okay, we're fine. Okay, everyone's fine.
I know.
I'm gonna move on. I'm gonna move on. This is my big point slide, guys. Big point slide. In this move to standardize algorithmic benchmarking, I'm especially talking to those of you who do technical work in here. Standardization is a lot of work. Our harness is not built for your tool, most likely. The harness may not work out of the box for you, and honestly, it probably won't. But we have shown how it can be adapted to all types of different tasks and models. So therefore, together, we build better. All right, I asked ChatGPT to do this. All right, thank you. So yeah, response once again, in terms of pull requests to the repo, I'd love to see your pull request to the repo. All right, and so I acknowledge all of these contributors. The ones highlighted here developed in a very big way to the algorithm track harness in terms of building the infrastructure, in terms of developing the metrics, and in terms of adding the data sets and baseline examples. All right, and of course, other things with the NeuroBench project, we have closed loop benchmarks via GIM integration that's in the works. We have this BioCast 2024 grand challenge with the motor decoding task, which has actually a very impressive amount of contributors. Common leaderboards and further results are coming soon. And eventually we'll figure out the system chart. So I will now walk you through this DBS gesture tutorial. I guess I won't run the code for sake of time, but okay. This is the libraries we're using, pip install NeuroBench, as well as a couple other libraries. And this is for DBS gesture. So your NeuroBench imports, this is your SNN torch model. We're going to get our classification based on the spike counts. So that's our post processor. And of course, the top level benchmark class, right? We define our model. This is very standard in Torch. It's a 4-layer convolutional SNN. It's a very standard forward pass. The model is loaded. So we're benchmarking our trained model here. So we have the model being loaded here, wrapped in the SNN Torch.
So the algorithm here is the model.
The solution, we would call the solution or the algorithm, yes, the model, the trained model. Network. Right, so the model is wrapped. Here is our data set, which includes preprocessors for turning the DBS gesture data into something which is consumable by the network. And this is wrapped in a very standard Torch data loader, which is going to be passed into our benchmark. Here for preprocessors, we don't need any preprocessors because the data library has already covered that. And our post processors is this choose max spike count.
That's an object?
Yes, this is an object. Our metrics, right now we have them defined as strings. You just write in what types of metrics you'd like. And all of this gets passed into the model top level. You call run, specifying your device if you'd like. And finally, it'll.
So the workload metric is accuracy?
Our workload metrics include accuracy, activation sparsity, and synaptic operations. Yes.
And how do you, and those are strings, but how do you know what strings you can choose? Those are names of your functions or?
Yes, those are names of our functions.
NeuroBench functions.
We have built up a lot of documentation on this, okay. So you'll find it. Yes.
Have you tested it
on anything to do like a simple comparison so that you know that,
So like
yeah.
verifying that if.
Well, yeah, just have you tried to run, one model and another model on exactly the same task because it's in your control?
Yes.
And were the results surprising? Can you share the results? Were they useful in some way?
In previous NeuroBench talks, I've always included those, and that's going to be when everyone's zoned out. So I didn't include those here, but if you'd like to see initial baseline results with all of the examples that I had shown on that slide previously, those are all available in our paper. Yes, so finally, after you call run, spits out your results. And you can parse these results if you'd like, but if you'd like more information, you can ask me. Benedetto will take over, and he's going to present L2MU, which was benchmarked using this harness. And for those, I think you can take a deeper look into the metrics and see how they are useful for benchmarking his
So it's very similar to what you get when you're using CubeMX, ST Micro, and you're doing development models. At the end, before putting in a microcontroller, it gives you basically a list like this.
That's right. That's right. Algorithmic complexity metrics working with them. All right.
Very similar to that.
So this is the end of my portion. I'm going to pass it off to Benedetto now, unless there are any further questions.
Hello. So I'm Benedetto Leto. I am a master's student here at Polytechnic Torino, and I'm here to present you how we converted a legend memory unit into a leaf-based legend memory unit. So what we use to benchmark this model is this dataset, the Wisdom dataset. Basically, it's a dataset where there are 18 activities that are classified into 3 main categories. There are 51 subjects, and each activity was collected for 3 minutes from the accelerometer and the gyroscope sensor. And they were with a frequency of 20 hertz. So the model that we used, the neuron models that we used to convert the legend memory unit was the leaky one and the synaptic one, and we used the SNN torch framework to adopt these models. So there was a previous attempt to convert the legend memory unit in its spiking version that I highlighted here in this research. I have to say that this version was converted using Nengo, and not only the components of the LMU were converted in spiking. Instead, in this version, though, I'm going to present you, we converted all the states of the model into a population of neurons. And yeah, so regarding the data preparation, we used only 7 classes. It is 36,000 non-overlapping sample, and we used a windows of 2 seconds from the 3 axes of the accelerometer and the gyroscope. So the training set is divided into 60%. The full data set is divided into 60% training set, 20% validation set, and the other 20% for the test set. So on the right here, I reported how the operation that are used by the standard legend memory unit. And on the left, on the right, I reported instead how we converted them into the spiking version. For example, if we take a closer look how the memory state is converted, basically in the legend memory unit, the non-converted one, we see that there is linear combination of the previous memory state and the input. In our case, instead, what we did is that this state became a population of neurons, and there is the same linear combination, but these 2 vectors here represents a vector of spikes. And in this case, what we determine with this linear combination is just the input current for the neuron population. That at that point, so we generate the spikes that are produced through the current as a neural input, and each state, each population has its own membrane potential, and the spikes are generated when the membrane potential overcome the threshold. So this is a representation of our spiking version of the legendary memory unit. So, and in this case, we adopted an encoding module. Basically, this encoding module serves just because we want that our network, the legendary memory unit, works only with spike tensor and not with raw data. So we adopted the neural network intelligence to execute the hyperparameter optimization. The model was trained for 300 epochs, and we used the validation accuracy as an object and as an objective, and the test accuracy for the final results. We adopted the two different neurons, as I said before, the leaky one and the synaptic one. And then there was post-hyperparameter optimization analysis that was done using different seeds. Okay, so at this point, what we wanted to do is to deploy the model into 3 different edge devices. So we exported the model using the Onyx framework, and we performed the inference using the Onyx runtime library. Also, we monitored the energy consumption and the RAM usage. So these results are pretty encouraging. This is a model that is not compressed, and we can see how we achieved a slightly better accuracy with the leaky neurons. And here, what we try to do is also how we try to compress the models. So we adopted the general magnitude pruning. And what we can see here is that the accuracy are, so we pruned the model, and then we fine-tuned for other 300 epochs. And what we can see here is that we obtained a slightly better accuracy for both models. And there was also the memory footprint that was reduced by 52% for the leaky neurons and 79% for the synaptic one. And this memory footprint was calculated as the non-zero parameters that we have in the model. And then also we can see how the synaptic operations that were computed through the NeuroBench library then were reduced also by 32% for the leaky neurons and 54%. At this point, we deploy the model. These are some of the results of this model deployed. We can see that the accuracy is slightly better for the leaky neurons, and the RAM usage is much better for also this kind of models. Okay, so the conclusion is that we converted the LMU components into its spiking version. And thanks to the SNN Torch framework, we compressed the models, and we can see that it's pretty suitable for IoT devices. And we achieved above 93% accuracy with the leaky neurons, and the inference time that was always lower than 300 milliseconds. And also one of the best models in terms of memory footprint and energy was also the one with the leaky neurons. What I want to show you now is this Jupyter notebook. And basically here, what I did is I instantiated three different models of the same architecture. One is in full precision, the other one is pruned, and the other one is quantized. So as Jason showed you before, basically what I did here is I defined metrics that I want to calculate, that I want to extract from our model. So I ran the benchmark for the full precision model, for the pruned model, and then for the quantized model. I want to say that the quantized model is just a first attempt, so it's not fully optimized. And what I want to show you here is that, for example, if we take in consideration the full precision model and the pruned model, we can see how the connection sparsity increased. And also, for example, if we take in consideration the activation sparsity, there is a little bit of increasement into the pruned model. And regarding also that we added another metric, that is the membrane updates, that basically counts the number of time that the neuron membrane is updated. So, and we can see here all these different results just leveraging the NeuroBench framework.
So you added a new parameter or a new class in your for the NeuroBench, which is
Yes.
Yes.
There is also, like, for the quantized models, we're still in the official library. We still don't support the matrix extraction from the quantized model, but we'll soon support it. So that's it.
Thank you. That's
Thank you.
That's wonderful, but it was too fast for me. Can you go back to your slide a little bit? It was just
Sure.
too much. It's a lot of good content. So what is the state of the art on this problem? You know, what is
So
the
we'll-
solution on this particular data set?
So what we want to do is that we want to classify these hand-oriented activities related to the general task. Basically,
Somebody has a smartphone in their pocket? In the pocket?
no, basically what we
That's it.
so what we used here is the smartwatch and not the smartphone. So these are like sensors that are extracted just from the
Oh, a
smartwatch.
watch. Okay, it's in a watch.
Yeah,
Okay.
yeah. Mhm.
Okay. But what's state-of-the-art accuracy and cost in this?
So
Yeah, what is that? Can you go back to that plot, which you didn't explain the axes? Yeah,
this
one.
one,
I can't read the axes. One is accuracy and the other one is energy per what? This
I
can't
think
read it. It's small for me.
joule. This is the joule.
Microjoule or something?
Microjoule, yes.
Microjoule. So,
And-
so most accurate solution is a vanilla or LSTM, right? Floating point LSTM,
Yes,
which
yes,
is
yes.
about 96%.
96% accuracy. Yeah.
Average accuracy. Okay, and then everything else is lower accuracy, substantially lower error, higher error rate.
Yes, but there is a much better memory footprint.
So everything to the left in that, and why is it colored yellow there? In the left?
I think this measures the number of operations. So in this case, the number of operation is lower than the CNN, and also here is lower than CNN. And in this case, we have a slightly better number of operations. I think this is measured in floating point operations. But this is our previous these are previous results, like made from another work.
Just close by the loop, you know? That's we all agree on that. Profile. Yeah. We agree. It's a very profile. That's what it is.